Okay, so here we get into part 2 of chapter 8. And we get into the normal curve, and so we're going to be extending what we did from part 1, and we're going to springboard off these continuous variables. We're not going to go back and look at discrete variables anymore. We're going to stick with continuous variables. And as we said in the previous presentation, chapter 8, part 1, we began to notice that if we take a sample from a population and measure them on a continuous variable, we begin to see not discrete scores, but rather a dispersion or a spread of scores. And this dispersion or spread of scores begins to show some form of a consistent pattern. And so we want to explore what this pattern is a little bit more so in the normal curve. As a matter of fact, the normal curve is this pattern. To a certain extent. But we need to put some definitions down, and then we'll get into some of the characteristics of the characteristics of the normal curve and how we use normal curve with respect to inference. Let's back the truck up here a little bit as we start into the normal curve. And remember that when we sample from a population and we're interested in assessing a particular variable, a lot of times what we do is we create a histogram, right? We do a bit of data reduction and condense all those individual values into these ranges. And when we plot these ranges, right, against the frequency, right, so here you see a bit of our histogram here on the left-hand side. You see the number of subjects. On the bottom, the value is diastolic blood pressure. A lot of times what you see in nature is this very bizarre hump-like pattern. I say it's bizarre because it does appear in nature time and time and time again. For the most part, sometimes there's going to be what we call the skewness of the data. It'll move to one side or the other. But for the most part, you see patterns like this. And again, just to draw our attention to this pattern a little bit more so, the things that we see in the pattern is this. We have very few scores on the high end of this dispersion and also on the low end. Most of the scores are in the center of this particular pattern. And so even though we have a dispersion, the dispersion begin to show some of these consistent characteristics. Low frequencies on the high end and low end of the scores, and the greater frequencies in the center or close to the middle of the set of scores. Now, the sample size also influences what this pattern looks like, at least in terms of either going from more of a jagged type distribution or spread to more of a characteristic that is smoother, so to speak, if you want to take a look at the pattern. And so we see in the first example here, still looking at diastolic blood pressure, when I've got a sample size of 56, we see that the pattern is it's not too bad. Kind of shows these classic peak in the center or most in the center and few frequencies on the ends. If we increase the sample size by more than 300, if we add 300 people more to our sample, we begin to see that even though you see some of the same patterns, right? If you take a look at the ends of the distribution, here, down the low end of diastolic blood pressure, we still have very few on the low end. We still have few on the high end, although it's a little bit higher than the low end. You still see that consistent pattern, but you see an awful lot more in the middle. As a matter of fact, this pattern begins to, if you want to characterize it, smooth out a little bit more so. You begin to see the smoothing of the curve, so to speak. This side over here is not so smooth. It actually looks more like a rocky peak. This here looks like the top of the Empire State Building, to be quite honest. At least part of it does. And the Empire State Building actually has smooth curves for the most part until you get to the very peak. So the pattern becomes clearer as the number of measurements or as the sample size increases. And if we can continue to increase the sample size and actually go right up and measure everybody in the population, everybody. So let's say that we were to sample the diastolic blood pressure from all Canadians, right? I think there's 37 million plus. The histogram that we have would smooth out very nicely. And this is what it would look like. The histogram would go from kind of jagged, because we have a smaller sample size here, 365, to over 37 million, we would see a curve that looks more like this. And so we begin to get our first sense of what the normal curve looks like. The normal curve actually represents the population distribution on a particular measurement. That's what that is. If we were to measure the entire population on some variable, height, weight, blood pressure, you name it, and if I were to measure all of them, if I could do that, then I would get a distribution that looks like this. It's very smooth. As a matter of fact, it's a curve-like pattern, and the curve-like pattern has certain qualities about it that we're going to describe even further. There's about three key characteristics of this curve that we're going to describe in the slides upcoming. And so we call this pattern or this curve the normal curve. And the normal curve really is a theoretical construct, right, that represents the distribution of scores on a particular measure from a population. That's what it is. It's a theoretical construct, and it's theoretical in the sense that it's almost impossible to measure the population. Right? It's almost impossible to measure everybody in the population for a variety of reasons. And so we use it in theory. We use it in theory, and we use it to do things like application. We use it to make predictions, and we can use sample sizes or samples to actually make these inferences or make these predictions or use these applications, because the samples, if we've seen even smaller samples, still look very similar to the normal curve. They're not perfect, right? But they're close. So later on in the course, when we start getting into t-tests, we talk about how we make some adjustments to some of the things that we use so that we can depend upon our sample size to represent the normal curve. That's off to the side for now. Right now, what I want you to know is that the normal curve is a theoretical construct that represents the distribution of scores from a specific population. Before we get into the further nuances of the normal curve and explain what it is and how it works, I want to describe it as a little bit further, and I want to describe it as a special type of histogram. Now with histograms, at least the ones that we've done in class, what we would do is we would create a class interval based upon a range of raw scores, and then we would post those raw scores in terms of those rectangles, so to speak, and we would see this distribution of class intervals. Well, we're doing the same thing with the normal curve, except the class intervals now are not the raw scores. The class intervals are set in terms of standard deviations. And if you notice, and actually that makes sense because the standard deviation really is a measure of dispersion, and the normal curve shows us this dispersion of scores. So we should use the appropriate units. That kind of makes sense. So if you notice here on this normal curve histogram, I'm not going to call it a histogram anymore, but here it is, you will see that we've got two things here. We've got the raw scores that are set, okay, and down below it you have the standard deviations. If you look up into the upper left-hand corner, you'll see that with this particular data set, the mean was 100 and the standard deviation was 10. So back to the normal curve, we see a mean of 100, and notice that if I move up one standard deviation above the mean of 100, I see a value of 110. That makes sense because one standard deviation above 100 is going to be 110. How do I know that? The standard deviation is 10. If I go 2 standard deviations above the mean, then I have a value of 120. If I go 3 standard deviations below the mean, I see a value of 30 because 3 standard deviations is 30 raw units. And so this is how this goes. We're not going to see raw units anymore. All we're going to see are standard deviations. Now, the other thing too is a score of 112 would be an example of some score that falls between 1 and 2 standard deviation units above the mean. Now, how many standard deviation units that would be is another question, and we cover that later on when we get to z-scores, because we actually convert standard deviations into z-scores. But this is what it would be. If I were to ask you where a score of 112 would fall based upon this histogram, you could tell me it falls somewhere between 1 and 2 standard deviations above the mean. Okay, so before we get any further with the normal curve, let's just take a step back here and just kind of get a sense of what the normal curve is telling us here, what it's trying to tell us. And we need to do that, we need to explain what is happening on the x and the y-axis, because really this is a type of graph. So on the bottom here, we're measuring certain variables on people, and so we're going to measure level of smartness and also height. So on the x-axis, we have this range. Close to the left-hand side here, we've got not so smart people, and then the far end here, we've got very smart people. It's the same thing with height underneath it. We've got some very short people here on the left-hand side, and on the right-hand side, we've got some very tall people. In the center here, again, we've got moderately smart people and moderately short, tall people, right? So these are our variables of interest, and these are the ones that are simply on this particular diagram. So that's the x-axis here. It describes what it is we're measuring, right? And these could be values. If this could be an IQ quotient, for example, if we're measuring intelligence, here we'd be measuring height. Those would be the variables. Now on the y-axis here, the y-axis is simply a frequency. That is to say, the number of times a score occurs. So if I were to say it was me here, and I'm somewhere between not so smart and moderately, this is where I would score here, and I would find that there's actually a fair number of people who join me. If I were to actually draw a line here and count out how many people still have the same level of intelligence as me, there would actually be a fair number of people who would be with me in terms of being, slightly less than moderately smart and a little bit more than not so smart. But again, we've got a larger range here in the center in terms of frequencies. So as we move along from left to right, as we move from not so smart to very smart, we see that the number of times or the number of individuals who fit this description begin to grow until you get somewhere in the center. And so we actually have most of the people, right, or the highest frequency of folks here are in the moderately smart category. The further we go in terms of smartness, we actually see that the further we get in terms of smartness, the fewer number of people that we see who actually fit that particular characteristic until we get down to the very end. It's the same thing with height. Okay, so this normal curve still has this pattern, right, of very few occurrences happening on the tail ends of the measurement, either in this case here really smart or not so smart, and most of the occurrences happening here where most of the values are somewhere in the middle. The key point again is to remember that the normal curve represents a frequency. And here's a bit of a hint coming up. With frequencies, if I've got frequencies, I can begin to measure percentages. Okay, so that's kind of a hint as to where we're going to go in terms of describing the normal curve. We're going to go from frequencies and begin to put percentages on here, but that's coming up in a second. One tiny thing to mention, and I'm not sure where to place this, I think it just had to do with how I had the diagrams here. But if you notice on the tail ends on both sides, I'm just going to use the right side for now, notice that this graph here, this end here, never really touches the bottom. Never really touches the bottom. Take a look, both sides here. Look on this side here too, right? It doesn't touch the bottom. It's called an asymptotic curve in the sense that the tail ends of the curve never actually get down to zero. Or the tails never touch. And the reason for that is this. Because it's a theoretical curve, the tails can't touch because in reality, we never really know what the true population dispersion or the true population scores are, right? We talked about that before. Logistically, it's really, really hard to know, and so we don't put that in. If the tails were to touch, we would then move into the realm of certainty, right? We'd know everything. If we knew the population, we would know everything. Because the tails don't touch, it leaves that little bit of uncertainty still left in there. And it's true, because we're not certain as to what the true population values are for variables for most cases, right? So anyway, it's called an asymptotic tail. That's coming up in another slide, but I kind of wanted to introduce it to you here. So here are the three key characteristics of the normal curve. I've already talked about the last one there, the tail aspect here. The tails are asymptotic. They get closer to the horizontal axis but never touch it. If they did, then we would know about the true population values. The other things about the normal curve, again, are this. The mean, the median, the mode are all equal to one another with the normal curve. And again, you could only find that if you knew the true population values, which you can't. Now, we've found that with some of our smaller samples that we've done with the data, very often the mean and the median are very, very close together. Okay, and so that's actually not too hard for us to kind of grasp and hold on to. The other thing about the normal curve is that it's perfectly symmetrical about the mean. Okay, which means if you take that curve and fold it in half, you could do it. Both halves would line up with each other perfectly. So the mean, the median, mode are equal to one another in the normal curve, and the normal curve is perfectly symmetrical about the mean. As a matter of fact, the mean is the center of the normal curve, as we're going to see in the slides coming up. So let's describe the normal curve a little bit differently. Not a little bit differently. Let's expand the definition a bit and be a little bit more precise. So here's our normal curve. The tails don't touch, so we know it's the normal curve. And in the center, now what we have is the value in the dead center of the curve. That's going to be the mean score. Now we know that every time we talk about the mean score, and any time we use measures of central tendency, we describe the dispersion of scores by using the standard deviation or some form of variance. In our case, we're going to use the standard deviation. And so on the bottom, even though I have these raw scores here, really, if we're trying to describe the x-axis, we don't describe the raw scores on the bottom. We actually describe the x-axis by virtue of the number of standard deviations that these scores fall from the mean. Now in this case here, we know that the standard deviation is going to be 10 because every standard deviation we see, every time it moves one standard deviation, we see an increase in the value of 10, right? Here's 110, here's 120, here's 130. And so we know that the standard deviation value is going to be 10. That's just the way the graph is set up. And we can see this on the reverse side as well. If we go below the mean, we see 90. 90 is 100 minus 10 is going to be 90. So that's one standard deviation below the mean, 2 and 3, and away we go. So for your benefit here, the raw scores are presented with the standard deviation. And from this, we can work out what the standard deviation is. The important thing to remember is that the x-axis for the normal curve is expressed in standard deviation units. You're probably not going to see the raw score. And that makes sense because we use the mean to describe the center of the normal curve, and the dispersion about the mean, or to describe the spread of scores about the mean, we don't use raw scores. We've always used standard deviations because that's our measure of variance. So then we describe the normal curve then in terms of the sample mean and its corresponding standard deviation units, notwithstanding all the other characteristics about the normal curve. Symmetry, mean, mode, and median lining up is the same, and also asymptotic tails. So here's some script here, and on the next slide I'll actually show you where these things fall. So let's say that I have a score of, I take a series of scores, forget about the sample size right now, and that set of scores has a mean of 100 and a standard deviation of 10. I'm using pretty much the same diagram as I've been using all along here. A score of 110 would therefore be classified as a score that was one standard deviation above the mean, right? So I take the score of 100 and I take a look at one standard deviation above the mean, which is 10. So that would give me a score of 110. Conversely, if I want to know what a score that fell, I could actually calculate a score that fell 3 standard deviations below the mean, using the same values here, the mean of 100 and a standard deviation of 10. I would know that 70 would be a score that fell 3 standard deviations below the mean. How do I calculate that? I take the mean value and I subtract 1, 2, 3 standard deviations from it, and I get a value of 70. And you'll see this on the slide next. Right, and so here we go. So here's our normal curve. We have our mean at 100. The standard deviations are also set. Normally you're not going to see those. You would see the raw scores. You just see the standard deviations. I'm showing you both just for this example. And so if I want to know what a score, one standard deviation above the mean was, if I knew the standard deviation, I would know that that score is going to be 110 because it's falling one standard deviation above the mean, and the standard deviation is 10. I add 10 to 100 and I get the value of 110. It's the same thing with the score that falls 3 standard deviations below the mean. In this case here, because I know the mean and the standard deviation, when I do my calculations, 100 minus 1, 2, 3 standard deviations, or 30 units, or 30 raw units, that would give me a score of 70. Okay, now I want to extend our knowledge of the normal curve a little bit. And we want to ask the question, well, what is under the normal curve? So far what we've seen is we've seen how the normal curve is expressed. We've got the mean in the center, of course, and then we've got the spread of the scores as defined by their standard deviation. And that makes sense because that's how we describe variance, is the standard deviation. But there's something else we're going to see now as well. And this is coming up on the next slide. And what we're going to see is we're going to see that each one of these standard deviation intervals tells us the percent of all the scores that fall between those certain intervals. Okay, so we call that proportionality. Under the curve, there's 100% of all the scores in that sample, right? However large that sample is, although we're going to talk about sample size coming up, that's an important part. But under the curve, we're going to see that within certain intervals, within certain standard deviations, right, between 1 and 2 standard deviations, for example, you're going to see a percentage sign. And that percentage sign tells you how many, the percent of the 100 of all the scores that have been measured in that particular sample. That's what that means. Now, the important thing that you need to know is this, and I've highlighted here on the slide in bolded white at the bottom. These proportions that you see in the normal curve never, ever change, right? They don't change. You'll see them, and I'll bring this up again and again. So we kind of hammer this home. Those proportions never change. Remember that we're working with a theoretical construct here. This is the normal curve. And so with the normal curve, we can kind of set rules. And this is one of the rules of the normal curve. The proportions that you're going to see coming up in the next slide, in between standard deviation intervals, they never change. So let's take a look at our first aspect of proportions here. And what we see again is we see these proportions that are laid out, right, in the normal curve. And notice that the proportions are associated with they're associated between 1 standard deviation units, right? So here's an example. If the normal curve houses 100% of all the scores, again, this is supposed to represent a population, and we somehow managed to find all 100% of the scores. 34.13% of all those scores are going to fall between the mean and 1 standard deviation above the mean. Okay. Now that changes a little bit if I go to, if I change the size of the interval. What if I said, well, what is the proportion of scores, or the percent number of scores that fall between 1 standard deviation above the mean and 2 standard deviations above the mean? Well, then that value is only 13.59%. Okay, and the further away you go from the mean, notice that the proportions actually decrease. Once you get above 3 standard deviations above the mean, the proportions of scores are very, very small. Now, this is above the mean, but notice that everything is mirrored if you're looking at the proportion of scores that fall below the mean as well. And that's because the normal curve has 2 mirrored halves of one another. So what if I were to ask you the question, what is the proportion of scores that fall between -1 and +1 standard deviations above the mean? Well, now I'm going to be combining proportions because I actually expanded the width of the interval, right, from -1 standard deviations to +1 standard deviations. And I want to know the percent of scores or proportion of scores that fall within this interval. So what I have to do then is I actually have to add them up together, and I come up with a value of just a little over 68.3% of all scores fall between -1 and +1 standard deviations about the mean. Now this is actually an important finding. What does this tell us about populations in general? It tells us that the bulk of all scores, 70%, close to at least, close to 70% of all scores fall between -1 and +1 standard deviations about the mean. So let's take a look at another example here. So now what I've done, I'm asking the question, what would be the proportion of scores that would fall between -2 and +2 standard deviations above the mean? And if I were to add up all of these proportions together under the mean, the value I would get would be around about 95.4%. So again, if the normal curve occurs in the real world, we now know with some level of certainty, okay, or some level of probability, how many scores are going to fall between -2 and +2 standard deviations about a particular mean, okay? And we can extend that even more so if our question demanded it, right? And what if I were to ask you how many scores, or the proportion of scores, or the percentage of scores fall between, where's my little laser pointer here, pardon me, the proportion of scores that fall between -1 standard deviation and +2 standard deviations above the mean. Okay, so again, I've outlined that by the red bars, and the value there, if I add up all these proportions together, I now get 81.9% if you want to round that up a little bit. And so we now know if these proportions of scores stay the same under the normal curve, and they don't change, remember the normal curve is a theoretical construct, then we can begin to get a sense of, well, almost a probability prediction, can't we? Remember, right? So the next slide's coming up, I want to make this transition and show you the logic in between proportionality and probability, because probability allows us to make inference. Now, before we get to the proportion probability connection there, I want to discuss with you what are called the cardinal rules for the normal curve. And these are classic. You're going to see these in pretty much every statistics textbook, and it's this. Under the normal curve, right, 68% of all the values, right, 100% of the scores, of the 100% of the scores that are there, 68% of the values fall between ±1 standard deviation of the mean, right? So if I had 100 scores in my sample, 68 of those scores would fall between -1 and +1 standard deviations about the mean. If I were to expand a little bit further to standard deviations, within 2 standard deviations of the mean, that's approximately 95% of the scores. And 3 standard deviations, approximately almost 100% of the scores, 99.7% of all the values fall between 3 standard deviations about the mean, ±3. So let's do a little bit of a transition here. Because, I mean, really previously, we didn't talk a lot about proportions, right? I mean, maybe when it was linked to frequencies. But with statistics, you know, the term that we like to use is probability. And so I'm building the scaffolding of knowledge for you for the normal curve by beginning with something that we know, which is proportions or frequencies or percentages. We can do that math. But now I want to show you how we can use the proportions under the normal curve to get to the probability or the chances of something happening. So here's the logic. Let's go and use these premises and build a logical model for how we can go from proportion to probability. Number one, in a sample, well, in particular our normal curve, I keep going back to sample and there's a reason for it, but let's go back to what I said at the beginning. With the normal curve, 100% of all the scores of the population fall under this range here, under this bell-shaped curve, right? We can agree with that. These scores are divided up into proportions or percentages based upon how many standard deviations they fall from the mean. And so we've broken those out now into those standard deviation intervals. For example, between the mean and one standard deviation, 34.13% of all the scores, of the 100% of the scores, are going to fall in those intervals. Okay, and those intervals, right, those proportions in those intervals never change. Let's go on to the next slide. So as I stated previously, the proportions, right, in terms of percentages, presented under the normal curve in standard deviation units, they never change. So it follows then that if the proportions never change, then we can begin to view them as probabilities, or the percent chance that a score will occur either in a certain point or within a certain interval along the normal curve, right? That's the logic. We accept the three previous premises, okay? And it follows then that if the proportions never change, then we can begin to view them as probabilities, or the percent chance that a score is going to occur somewhere along the normal curve. So here's another way to describe it, right? So on the example below here I have, there's a 34.13% chance that a score will fall between the mean and one standard deviation from the mean, whether it's above or whether it's below. Remember, the normal curve is symmetrical. If we know the raw score value and the mean and the standard deviation, we can use the normal curve to answer that question. What are the chances a score is going to fall between 2 and 3 standard deviations above the mean? I can now begin to take a look, going back to the normal curve, and take a look at the proportionality. And it's a little over 13% in that case, isn't it? Right? So this is how we begin to use the normal curve. We've now gone from proportion, right, to probability, and I want to show you why that is. So here's a different way of asking the question. What if the question I asked was, what are the chances that a score will fall higher than 2 standard deviations above the mean, or be higher than 2 standard deviations above the mean? In this case here. Well, again, I go and I take a look at draw my red line there, because that's where positive 2 standard deviations is. And I simply begin to add up the proportions of the scores that fall above 2 standard deviations, and I come to a value of 2.28%. So the answer to my question, what are the chances a score is going to fall above 2 standard deviations above the mean? The answer would be 2.28%. Now that's actually a really, really low chance. You know, another way of saying that would be, what are the chances a score is going to fall below 2 standard deviations above the mean? Well, we subtract, I'm just going to round up to 2.3% for my own math. If I subtract 2.3% from 100%, what do I get? Help me out here. Is that 97.7%, I do believe? So there's a 97.7% chance a score is going to fall below 2.2 standard deviations above the mean. Right? So now we begin to take a look at chances of things occurring. And again, it takes us back to that question I asked you before. At what point do you put money down before you make a decision on whether or not you think something is going to occur or not? Remember, because there is no certainty. Right? How close do you get? So in this case here, what are the chances that a score is going to fall above 2 standard deviations above the mean? Really, really low. There's only a 2.3% chance that's going to happen. That's not a lot. That's not a lot. And I want to take this now and extend it a little bit further with you. So I'm in a bit of a preamble here, and we'll cover this when we get to z-scores, but I kind of want to show you where we're going with this. And maybe the best way to do it is to show you an example. So let's say that I've got two midterm scores, right? So midterm 1, the class average was 62.1 out of 100, and the class average for the midterm 2 was 72.8 out of 100. Now, that's an increase of over 10 points, right, or 10 percentages. Okay, so let's also assume that the course content difficulty doesn't change, nor does the midterm format, and so we've controlled everything as much as we can. And we still see an increase in the midterm scores. Now I could ask you, what do you think happened? Well, there's a bunch of different things that could have happened. But let's just say that we hypothesized about something. Let's just call that hypothesis an intervention. Okay, that intervention could take place either with, well, increased studying or perhaps increased cheating. Okay, one of the two would still answer the question. All things being the same, there might be something else that could cause that change. And what do you think that something else is? What do you think that something else is? Right? Begins with a C, ends with an E, and the answer to that is chance. Okay? So researchers begin to ask these questions. When we see changes in scores, the question the researcher has to answer is, did this change occur, right, by chance alone? Because chance can happen, that's the only thing that is certain. Or was it due to a particular intervention that took place? A lot of times in research we call these things interventions. Often it's called the independent variable. That's the more technical term for it. But something else outside of chance that might influence the score. And so, again, the question is, are the improvements that we see in the midterm scores due to chance alone, or were they due to a particular intervention that took place? In this case, well, maybe it was studying, right? The professor kind of came out and said, hey, look, you guys need to study a bit more for this exam, right? Or the students kind of went, oh, I need to study a bit more for this exam. And so the next slide, I want to show you what this might look like using the normal curve. And so here's our two scores, right? When we take a look at the distribution of the scores, remember a midterm score is a continuous variable, and so it's going to fall along the lines of a normal distribution, as we've been seeing. It's not a nominal score, it's not an ordinal score, it's a continuous score. And so we see here the two different means, right? The initial mean, let me just get my little pointer here, the initial mean of the score, right, was 62.1, and the second midterm score was 72.8. Now we know that there's a certain probability of scores that are going to fall if we use the normal curve. And the question now comes down to this, and this is where I'm going with z-scores in the next round of slides, the next presentation, is this: how far apart do these two scores have to be before we say, you know what? Really, really small chance the 72.8 actually occurred by chance. Okay, and if you notice where this, I don't have the standard deviations lined out here in terms of numbers, but look how far apart the 72.8 is compared to the 62.1. We're getting close to what, maybe 3 or 4% of the total scores might fall on this side here. I mean, how far apart do you have to be from your original mean score, right, before you say, yeah, you know what, it's a really, really small chance this second midterm occurred by chance. As a matter of fact, what we're thinking is that the second midterm score occurred because of something else outside of chance. And so researchers have to set certain thresholds before they say, yeah, you know what, this could have happened by chance, right, looking at the normal curve here, but the chances it happened by chance are really, really small, right? Go back and take it now. If we knew what this was in standard deviations, it'd be easier for us to make a decision, right? You might say, well, what if this was, 2 standard deviations above the mean? Well, now we know there's a very, very small chance, like less than 3% chance, this value happened by chance. Is that enough for us to say that it was the intervention that caused the differences in the scores? That's where we're going to. Okay, and I'm bringing this up now because I'm going to introduce it to you, and then I'm going to reinforce this as we move forward. So if this whole thing of the normal curve was a Black Forest cake, which I love, by the way, they're incredibly tasty. We're sort of getting near the end. We've kind of baked the cake. We've put on the glaze, whatever it is, and now I'm adding the chocolate sprinkles and the maraschino cherry here to kind of tidy up a little bit. Not tidy it up. You just can't have a Black Forest cake without chocolate sprinkles and maraschino cherries. Anyway, we need to come back to the sample size and how it relates to the normal curve. Remember that with statistics, we base part of our statistics that we use on inference, right? We take from the sample and infer onto the population. But the normal curve, right, is supposed to represent the population, right? It's a theoretical construct where we've got everybody in the population and we've got these proportions. But we also know that sample sizes vary in size. Some samples are very small, some samples are very large, and the larger the sample size is, the closer we get to that population. So we need to look at a few caveats here, okay? So this is something that we need to consider, and again, from the previous slide. The number of individuals we have on our sample, right, begins to dictate what that sample curve is going to look like. And so we see here on this slide, obviously a sample size of 1, I mean, it is the curve, right? We call that a case study. And we've got a sample size of 2 and a sample size of 10. Notice that once you get around about a sample size of 25, some textbooks might say a sample size of 30. Once you get to a certain sample size, again, this is randomly chosen too, okay, ideally, we begin to see that the distribution begins to mimic the normal curve a lot more. So there's something to be said about the sample size that we choose in terms of our predictions or our probability predictions. Okay, we can't forget that. And that's why I brought up sample size before. Right? The sample size influences our inference. Right? A larger sample size is much better than a smaller sample size. Now, for some of you who have taken research methodology, we know that there are certain things you can do with smaller sample sizes to give us greater confidence. I can't go into that right now. I'm sorry. I'd love to, but I can't. So for us, what I want us to focus on is the size of the sample, because that comes up a little bit later on when we get into t-tests, and in particular something called the standard error. That's coming up a little bit later on, but that's coming up, well, pretty soon actually. I'm not sure if I've mentioned this before, and I apologize if I'm throwing a curveball at you, but I wanted to make sure that we understand that in this whole aspect of inference, sampling, and population values, that it's really hard to know in real life what the population statistic is, right, for something. So, you know, for example, weight. What is the weight of Canadians on this day that I'm recording this PowerPoint? Well, who knows? You know, it's changing. I mean, somewhere in Canada, someone is eating breakfast, right? Or drinking a beer or something like that. They're actually adding weight to themselves. And so, you know, if the population statistic, which we call a parameter, by the way, if the population parameter is fluid, then how would one ever know what a population value is for a particular variable? It's going to be changing all the time, and especially if you want to go down to a real precise measure. And so this is why we pay so much attention to our sample. And this is for me, when I critique a journal article, I go right away and I take a look at, number one, how many people are in the sample, and how did you get the people into your study in the first place, right? That's your sampling technique. That's what I do, because that feeds me some information about the strength of the study. But it kind of takes us back to this, the question, can samples then really represent the population? Right? Especially if they're smaller than the population, and especially if we don't know what the population parameter is, right? If that's hard to ascertain. And so it's almost like, you know, we're nailing Jello to a wall here. It's like I'm asking the impossible. I'm asking you to kind of put together in your head something that is, you know, cobbling together is quite challenging. Well, join the club. We're all in this together, right? Maybe a better question might be this, you know, how likely is it that the sample represents the population? And we're going to get to that. We're going to come to something called the standard error and confidence intervals. That's coming up in chapters 8 and 9. And we'll talk about that. The next slide I want to show you is more of a visual demonstration of this sample population inference thing. So here's this visualization of what I was chatting about on the previous slide. Right. And what we see here in this particular slide is we see two different curves. Number one, we see the population curve or the normal curve here, right? And here's the mean. The mean for the population curve is called mu, I do believe, right? And the population standard deviation is called sigma. Again, that's just another symbol. But again, the population actually represents the real world, and I put this on here, unknown to us, because it's really hard to know what the true population value is. We know it's out there, but it really is unknown to us for reasons given previously. Now, the other thing we have superimposed on the population curve, or the normal curve, as we call it, is the sample curve here, right? And the sample here is represented by a value that we do know, right? Or the symbol that we do know, that's the mean, x with the bar over top of it. And here's the mean value for our sample. And again, we've got the standard deviation symbol is the small s. And notice that the sample is actually close to the sample mean here is close to the population mean, but it's not quite exact. Well, that's normal and that's to be expected. You know, let's just say that this was a sample size of 100, and I took them out of the population, measured them, found this difference here. It's pretty close, but it's not exact. And I take this 100 individuals, throw them back into the population, and then take another sample of 100 and measure them again. What I might find is a similar sample curve, but then the mean might fall maybe only slightly to the left of the population mean, so it's a little bit less. Okay, I take those same 100 individuals, throw them back in the population, sample them again, and that sample might be pretty darn close to or almost exactly to the population mean. I mean, these things can happen. Okay, so the sample mean very often, depending upon the sample size and how I sample, can actually be pretty close to the population mean, even if I don't know what the population mean is. And you're wondering, how can you do that? We're going to get there. I'm just showing you here the complications and the complexities of linking samples to population, right? Because we depend upon inference, right? We take from our sample that we can measure and infer to the population that we really can't measure. And then we have to be confident in this. And again, this is why with statistics, we don't use the word prove, okay? We don't use the word prove because we are taking very, very small leaps of faith here. I'm going to talk about faith a little bit later on in science. Okay, but again, we have to pay attention to this linkage between samples and population. They're not going to be exact, right? But we can still be confident that we can actually make statistical decisions and statistical conclusions, and that's where we're moving to in our course. Yeah, okay, this has nothing to do with statistics, but I always kind of like this slide. It's not the normal curve, it's the McDonald's curve, right? Switching from never again to I'm loving it. Ever been there? Do you eat McDonald's? I still think they have the best fries, by the way. I know it's, you know, they're cheap as borscht, but I still think they have the best fries. Anyway, let's get out of here. So let's summarize here. We've covered a fair amount of ground. So let's put this into some bite-sized pieces in terms of what we covered with this section. So the first one is the sample data, especially if it's a continuous measure, follows a particular spread or dispersion pattern when we measure them. Right? We saw this with histograms, and now we've seen this more, especially if the sample size gets larger, we see this as more of a normal curve. We use sample data again to represent the population data. This is called inference. And I keep coming back to this because this is that second half of statistics. This is what we use the normal curve for. So when we assess the probability that a sample mean represents the population mean, we have to include the standard deviation as part of that assessment. It's not just sample mean and population mean now. We also have to include sample mean and standard deviation along with population mean and population standard deviation. So we've got to look at these things in terms of their pairings. So what do we use then to use inference here? Well, to use inference, we use what is called the normal curve. Again, it's a theoretical construct, right, that represents the population mean and the population variance. The normal curve is symmetrical about the mean, and the spread of the scores of the variance is described in standard deviation units. So carrying on with our summary here, the normal curve is divided up into proportions that exist in between these standard deviation intervals, right? For example, we saw that between the mean and one standard deviation, that's where 34.1% of all the scores are going to fall. And these proportions in between these standard deviation intervals, they never change, right? They never change. So logically, it follows then that if the proportions never change, then we can use the normal curve to make probability claims, right? There's instead of a 34.1% number of scores fall between the mean and one standard deviation, we can say there's a 34.1% chance a score will fall between the mean and one standard deviation above the mean. And so this is why we can use things to infer, to make predictions or claims about a population using the normal curve. And because the sample data represents the population data, again, we can infer these probabilities from the sample to the population. And this is where we kind of come back to this term inference. It all goes back to inference, inference, inference. But to have inference, you've got to have a sample that represents the population, and this is where it gets a bit more complex. The rabbit hole is getting a little bit deeper here, and yeah, we're going to carry forward with this and go through some things after z-scores, which is the next section coming up. We're going to get into things like the standard error of the mean and confidence intervals. And that tells us more about the relationship between the sample and the population.